Go.
I'm ready. Thanks, Marcus.
Fantastic. All right. Good afternoon, everybody. Good morning, everybody, depending on where you are. My name is Marcus Wagner. I'm here with Monash University on Monash University campus. It's my absolute pleasure to be introducing to you today Associate Professor Aldeida Aleti. He'll be talking to us about testing autonomous vehicles, a topic that she's been working on for quite a number of years now. Maybe briefly on her background, she's done plenty of work in the software testing space, in the optimization space, in the search-based software engineering space, so working there at the intersection of software systems, software, and typically heuristic optimization. I've just gone through my emails. Apparently, Aldeida and I, we've met the first time in about 2016, so we go back quite a few years. Yeah, she's written many papers. I saw the top-cited paper has about 400 citations, which is a fantastic achievement. And a number of years ago, she was awarded by the Australian Research Council a DECRA, so one of those 3-year fellowships that let you do whatever you want for 3 years, pretty much. With this brief and insufficient introduction, I'll hand over the stage to Aldeida. So yeah, take it away. Tell us about all the cool stuff that you've been working on recently, or maybe all the stuff that you plan to work on very soon.
Yeah, thanks, Marcus, for the kind introduction. And hi, everyone. Thank you for coming to this presentation. As the title of my talk says, I'm going to talk about optimization for testing AI-based systems, but with a particular focus on self-driving cars or driverless cars. This is a project where I have a team working on this, Nilofer, who's a research fellow, and Victor, who's my PhD student. So most of the work that I'm going to present here today is in collaboration with them, or mainly driven by them. And I will mainly focus on the driverless cars, but I will touch on the general topic of AI-based systems testing. What does that mean? How are those AI-based systems different from from traditional software systems, and what kind of new challenges they present in the testing space? I'll keep my talk high level, but happy to go into more details. And feel free to ask questions throughout the presentation, and I can go more in more details. Okay, let's start. So we are yet to see the first fully autonomous car. We have some examples of self-driving cars around, some good examples, but their scope is quite limited. But I don't know if you remember in 2015, there was a big hype about self-driving cars. There were quite a few companies, such as BMW and other big companies, that were saying that in 2020, we will mass produce self-driving cars. People will be driving or not driving self-driving cars in the road. And that hasn't happened. So we haven't seen those self-driving cars yet. There's still companies working on them, but it's proven to be more challenging than what we anticipated. There are studies, however, that show that self-driving cars are safer than human driving. This is a study that was conducted very recently. And as you can see in this graph, we have the blues. So there's 2 different ways of measuring collisions, and the lighter blue one is a bit more refined. So the blues are human-related collisions, and the red one is automated driving cars. So the automated driving cars, they result in 65% fewer collisions, 94% fewer collisions with primary contribution, that is them causing the collision, and 74 fewer collisions with meaningful risk of injury. So they are safer. However, they're not there yet. And one major problem is that, especially when they interact with each other, they cause lots of problems. They cause gridlocks, traffic. They, in particular, when the sensors don't work as properly, they stop and they don't move. And so they try to avoid these collisions, and they're not as effective in driving. This was very recently. This photo is taken very recently, where a fleet of autonomous driving cars caused a big gridlock. I think this was in LA. The reason is that a big bottleneck for self-driving cars to be commercially viable is testing them and making sure that they are safe. This is the main bottleneck. It incurs high cost and significant time to test them and to ensure their safety. Just to give you an example, for human drivers, there's usually one or two accidents for every 1 million miles. I'm using miles, but so is it 1.3 million kilometers? I don't know that conversion very well. And a fatality for around 100 million miles. So to fully test the self-driving car, we need billions of miles to test them and to make sure that they're better than humans. And this is quite significant. It's a big cost. And at the moment, at the current rate, what the self-driving companies are doing, so from 2019 to 2020, in 1 year, the testing of a self-driving car, the amount of miles that a self-driving car was tested is around 770,000, one of the highest miles that were used to test the self-driving cars. So, compared to the billion miles that we need, this 770,000 is really a drop in the ocean. So it's quite expensive. It takes a long time, and it's also incurs some safety concerns. So how do we give a driverless car a driving test? So how do we ensure that they pass that driving test? Fortunately, we have simulations, and they are very high fidelity, great simulations. They're used by companies that are developing these self-driving cars. Carla is one of the open source examples that we use in research as well. So we can simulate real scenarios, close to real. They're simulations, but they're very realistic, where we can have a self-driving car interact with various actors such as humans or other cars, other intelligent cars. So this is will reduce significantly the amount of in-field testing that needs to be done. Of course, that is still necessary, but we can perform simulation testing to at least catch some of those initial bugs, and reduce the amount of testing that needs to be done in real scenarios. So one of my students, Victor, he's working in this area, and he's developing search-based techniques for simulating, and this is a screenshot from one of his simulators using Carla. He's simulating different driving scenarios, and his focus is mainly on how to create bad drivers that drive other cars, and test whether this self-driving car can indeed perform the right action to avoid those collisions. And these, for example, in this case, what Victor is doing, so a solution in this case would be the velocity so the solution representation of these variables, such as the velocity of the other cars, the direction, the different maneuvers, for example, changing lanes, and the goal. So each of these points, represents it. So each of these red points represents the goal that the self-driving car needs to go to. So he's using a genetic algorithm that searches the space of possible solutions and identifies and optimizes them to as an objective function is the minimizes the distance between the self-driving car and the other and the other vehicles, but also the number of maximizes the number of collisions and also minimizes the time to a collision. In particular, the solution that Victor is developing is looking at how do we, so in previous work, other researchers have used genetic algorithms and other approaches to optimize the behavior of other cars. However, they've looked at a more granular level, and that creates an explosion of a search space. So Victor now he's looking at what is the right level that we need to define these actions in order to find solutions that reveal this incorrect behavior of the cars in a more efficient and effective way. This is one piece of work, and I just wanted to give this as an example of how optimization can be used for generating test scenarios for self-driving cars. It's been quite an effective approach. Other approaches I mentioned search-based software testing that can be used to generate such scenarios. There was a recent paper published in Nature where other researchers are using realistic driving scenarios. So there is available data there of realistic collisions and real collisions and real driving cases where there's been a collision, and they're training deep learning models on those data and then using those deep learning models to create driving scenarios. So there is a whole area where researchers are looking at machine learning to generate test cases for self-driving cars. Those are quite computationally expensive, in particular training these models, but also generating those test cases. Whereas with using search-based software testing, this is a more lightweight and it can prove effective, in particular to identify those effective test scenarios that can reveal errors. In the future, we're also planning to look at how we can identify significant features of driving scenarios that can be used to generate new scenarios. And I'll touch a little bit later on in another piece of work we've done. But that's also quite an interesting area because not all features of scenarios result in incorrect behavior. That could be, for example, and in this case, we haven't looked into those kind of things, but for example, weather conditions, or it could be the shape of the road. So more looking at also the particular maps and other features, not just the features of the other cars, and identify what are those effective features that are more impactful in revealing incorrect behaviors. Now, we're looking into the testing of self-driving cars, but the question then is, well, how do we know that we've tested enough? How do we know that we've identified, all these key test scenarios that are needed to test a self-driving car? And what other scenarios are needed? What have we missed? And how can we improve the test suite that's being used for testing a self-driving car? What kind of test cases are missing? And so this is important because often, I guess, in particular with search-based testing techniques, they focus on test cases that are likely to reveal bugs. And so once they identify a particular test case that's has identified a bug, then they keep using it in the population to generate new test cases. And after a few iterations, then the population becomes more and more homogeneous and losing some of that diversity. So that at the end, the test suite that we end up with may not have considered all possible important scenarios. So adequacy criteria for telling us how good the test suite is gives us confidence in terms of how well autonomous vehicle works. And it's not just in the area of AVs, but in testing in general, and in particular also in AI-based testing, in testing of AI-based systems. It's important for us to understand how well we've tested a particular system. In previous work, with in testing, usually what we use is coverage and diversity as two of the key adequacy metrics to tell us how good a system has been tested. So coverage looks at, so we have metrics such as line coverage, method coverage, and other, variations of these coverage metrics. In AI-based systems, there's work that uses neuron coverage. So how well have we covered the neurons of a model? And if we have achieved 100% coverage, then it is in a way some guarantee, well, not a very good guarantee that at least we've kind of covered all the lines of code. Previous research shows that coverage doesn't correlate with ability to detect bugs. So covering 100% coverage doesn't necessarily mean that we've discovered all bugs. And diversity focuses on the either diversity of the input or the diversity of the behaviors that are discovered from the input, so behaviors of the self-driving car. These metrics are not always suitable for AI-based systems, and new metrics are needed to give us a bit more comprehensive view, but also they don't tell us so when should we stop testing, and what kind of new test scenarios do we need to complement the existing test suite. So this piece of work was done with Nilofer on using instance space analysis, which is a technique developed by Kate, but we have applied that to the area of testing. This paper will appear at ICSE soon. And what we are doing here is that we are using instance space analysis to an input of an instance space. I probably won't go into too much detail of instance space analysis, or I will explain how we've used it. So the idea is that we want to see how the test suite, how well the test suite, how good the test suite is, and what are some of the areas that have not been properly areas of the instance space. And an instance space, in this case, each point here is a test input, and we then characterize each test input with features such as, in the case of a self-driving car, a feature of a test input could be the weather conditions, could be the road conditions, could be also the other vehicles, the distance from the other vehicles at the start, the velocity, and so on. So we have a large set of different features that characterize each test input. And then we use instance space analysis to identify those significant features that can best separate effective test scenarios from the ones that are not effective. And effective in this case means test scenarios that are able to reveal incorrect behavior in a self-driving car. And the instance space analysis creates for us these footprints where we can see the separation between the blue points, which are the effective ones, and the red points, the non-effective ones. And instance space analysis also draws this boundary for us, which tells us, well, this is the possible test scenarios that you might consider that are feasible but haven't been generated, and tells us about the areas where we have not generated test scenarios. This can help identify how good a test suite is, but also guide the generation of new test cases. So we looked at different metrics. We call them based on adequacy metrics that were based on instance space analysis. And so we've used here, for example, the area bug is the area of the instance space where we have where test cases identified a bug in the system, and there were coverage is also another metric that was based on the instance space analysis, which is the coverage of the instance space, which is, the area of the instance space as a proportion of the whole possible space that we could have explored by generating test instances. And we looked at how these values correlate with bugs. That is, if they highly correlate with whether the test suite identified the number of bugs that were identified by that test suite, then it's a reliable adequacy metric that can tell us, the higher values of that metric means it's a better test suite. And other metrics, such as existing metrics, such as the diversity based on Shannon's entropy and other diversity metrics and coverage metrics, they didn't correlate as highly as the area bugs. That is the area of the instance space with instances that identified a bug. This the existing metrics, they focus either on diversity or on coverage. The strength of instance space analysis and the metrics that it was able to generate is that these metrics are a combination of both. They give us information about the diversity of the test cases, but also around the coverage of possible test scenarios that we might be able to generate for a software system. So that's the powerful aspect of it, and why it can correlate so well with the number of bugs that we find. Another problem in testing software in general, but in particular AI-based systems, is the test oracle problem. And I will not go in very much details here. I wanted to mention this as this is quite, in my mind, one of the important problems that we need to address when it comes to testing AI-based systems. The oracle problem is the mechanism or principle by which we determine whether or not the software under test is behaving reasonably. That is, checking the output from a test case and determining whether that is correct or not. Now, in many cases, the oracle could be an exception, or more often, is the oracle is the human that needs to look at the output and determine whether the system behaved correctly or not. When it comes to AI-based systems where the input space is quite large, determining the correctness of the output is quite a difficult problem, time-consuming, quite computationally expensive problem. And this is known as the test oracle problem in testing. It's been researched from before we had AI-based systems. And I use the term AI-based systems. This is a term used in software engineering for systems that have an AI component. And I have a graph there later on that I will touch into that, but the AI component usually in these systems is only part of the whole system in terms of lines of code. Is just part of the system. So the test oracle problem is exacerbated in these systems, particularly when we think about generative AI and the very creative outputs that generative AI systems produce, the question of determining whether that output is correct or not becomes even harder. It's very hard to automate the test oracle problem. Often you need a human to look at it. There are some approaches in generative AI systems testing that automate this process, although they're limited. Those approaches focus on developing knowledge graphs. They develop knowledge graphs on knowledge, like for example, Wikipedia. Wikidata is in a particular knowledge graph, and use those knowledge graphs to generate test cases. And they can automate the labeling process in this case, because the knowledge graph tells them what the relationship between data. So for example, it could be Melbourne is a city of Australia, and then they generate test cases such as, what is the city of Australia? And then they look at the output from these generative AI systems, and if the output is Melbourne, is correct, and they can check that by looking back at, they can create those automated oracles by looking back at the knowledge graphs and checking whether the output was correct or not. Some other approaches focus on metamorphic testing. And metamorphic testing, you define these metamorphic relations, where you look at a metamorphic relation, for example, in a self-driving car, can be when you, given a particular test scenario and you look at the behavior of the car, for example, recognizing a stop sign and stopping, then changing the weather conditions, that the behavior of the car shouldn't change. It still should stop when it sees a stop sign. So by defining those metamorphic relations, then we can automatically check the output by looking whether the output changes or not. And if it doesn't change, then the behavior is correct. But those metamorphic relations, still, we can define them in particular context for particular cases, but not for all possible scenarios. So still the test oracle problem remains, and the human is the oracle, which makes this quite a difficult problem. Now we've done some work in this space, and we have a paper on the automating, learning this test oracle problem, not in the context of AI-based systems, but we're looking at how this can be automated for example, testing generative AI systems and through interaction with human. Now going back to AVs, just now in these few slides, I will just go through some concepts around testing AVs and some of the areas that we look at, and so the different levels that we look at for testing AVs. AV systems, they have these AI components, and there's different ways of developing these AV systems. There's companies that develop each of these AI-based AI components. For example, the perception and localization component, the high-level path planning, the more low-level path planning, motion controller, they are developed independently. They are trained and tested independently, and then they are put together, and there's done system-level testing, then is performed at a higher level. And more recently, there's this end-to-end learning, recognizing that that there is an interaction between these components. So in the first approach, there's a different objective function for each component. So when we optimize one, it will have an impact on the other. In the perception and localization, precision is the main objective, but in the low-level path planning, then there we focus on safety and comfort. So how do we then ensure that when we look at safety, that overall, when we put these components together, they're still we have a reliable car. So this end-to-end planning addresses that problem and looks at how do we train these components simultaneously and test them simultaneously. And the types of testing that we do can be at different levels. There's white box text testing. I mentioned in one of my previous slides as the coverage criteria looking at neuron coverage. So these white box testing techniques, they assume that there is model architecture and we have access to the weights and the hyperparameters and the neuron activations. So then we're able to, given a test input, we are able to calculate the neuron coverage and optimize the test inputs to maximize neuron coverage. Often we don't have them available. So data box testing is another approach that assumes that we have the training set and the test set, and they are used as an initial feed to the test generation. And black box testing is the most common approach, where the trained model is considered as a black box. We only look at the input and the output. We cannot calculate coverage measures in this case for the model, but that's the most common approach. I talked a bit about, briefly mentioned the AI-based systems and how this ML code is one component of the rest of the software system. And the size of the box here is an indication, and this changes from system to system, but an indication of how many lines of code are usually part of this ML code with respect to the other parts of the software system. So it's only one component. The rest is things around model analysis, process management. There's a lot of code that's written to build an AI-based system. Hence, in software engineering, so there's approaches that focus more at that model-based testing, model testing, but more and more we're going in the direction of looking at the system level and testing the whole system. So this is a review of the current state of the research in terms of the number of papers that have been published at each level. So the input, model, system, and the integration at the end. At the moment, many approaches are at the model level, but this is shifting towards the system level. So historically, when we look, many papers have been published at that model level. There's now an understanding that we don't have access to the model level, and in particular, there's, I guess, the model level testing is probably not always available. I mentioned that I would touch a bit also on the AI, why bugs in AI-based systems are different to traditional software systems, and why we need new techniques and why we're working on new techniques. And what are some of the characteristics that are part of these AI-based systems that are not in traditional software? So one of them is the data dependencies, and this refers to the fact that we might have the same lines of code, but if we train that model on a different data set, then we will get a different behavior and thus different bugs. So this data dependency is a new problem for software engineering, and how do we then detect those kind of bugs and how do we repair them can be quite challenging. The lack of clear outputs and ground truth. This refers to, in particular, when it comes to generative AI, the output is creative, it's new, hasn't been seen before. We don't have a ground truth. When we are looking, for example, at classification systems, we have existing data that tells them, given a particular input, what's the class that it belongs. With generative AI systems, that doesn't exist. And thus, when we're testing, we need that ground truth. And often that becomes, and this is related to the Oracle problem, often we need a human, but even when it's a human, particularly when the testing objective is not correctness, but it's more not as other objectives, such as, for example, biases or fairness, then that makes it harder. The complexity and the behavior is difficult to understand and predict, and thus these systems are difficult to debug and identify where exactly is the error. The non-deterministic behaviors, they produce different outputs for the same input depending on their internal state and the initialization. So how do we then, again, debug them and fix the bug? Lack of interpretability, again, this relates to the debugging, and the large search space of possible inputs. How do we generate effective test inputs? As generating all possible test inputs, it's not feasible. The kind of algorithms that are used in the literature, there's most testing approaches, they're mostly domain agnostic, but there's quite a large number of papers that focus on autonomous systems, and a few on classifiers. These are papers published in the software engineering community. I'm sure there will be others in AI community that are not part of this literature review, but in software, the main approaches are domain agnostic. And the testing objectives, correctness and failures is the traditional and the most researched testing objective, and the works that I showed at the start of my talk focus on correctness, that is correct behavior, that is collision or no collision. So we, for example, for autonomous drivers, we want to have a car that doesn't collide with other cars. But there are other testing objectives that have been used, such as robustness to noise or adversarial attacks. And a lot of work in software engineering is focused on how do we mutate, or how do we change inputs so that to reveal and introduce noise, in particular in image processing systems, so that to change their behavior, we want them to be robust, and thus we generate these adversarial inputs and use them for retraining and to increase the robustness of these systems. Fairness is also, in particular, recently there's significant research in this area around the fairness and biases. So fairness testing is called the area, looking at different protected attributes, gender, race, country, age, and so on, and making sure that these systems are fair and unbiased. And there's been significant press even recently around issues around biases. And so this work, and I'm going to show one work that we've done in this area in the next slide, how do we ensure that these systems are fair? Efficiency and performance is important. So we might have correct behavior, we might have robust, fair systems, but then particularly when they are put in production, they need to be efficient and perform well. So you might recall when the ChatGPT was initially deployed with the increase of number of users, then there was a low response rate and quite significant delays, and they had to change quite a few things to make it more efficient and perform well. So one work that we've done in terms of this fairness objective is in collaboration with some hospitals. We developed a wait time, the wait time prediction system that was deployed. It's currently deployed in a few hospitals here in Victoria. And the wait time prediction uses ambulance data to train a model and look at the wait time and develop a machine learning approach that can use patient information in terms of their illness and time that they come to the emergency departments and other features to predict the time, how much they would have to wait. This is important for scheduling purposes and prioritization, and also to tell, give the patients some information around how much they have to wait so that they can decide whether to go to another clinic or not. And we were concerned that this weight prediction system would, weight time prediction system would have inherited some of those biases that might have been in the data. And so we developed this approach, a search-based fairness testing approach that looks at, looks at a particular, generates a patient based on existing, generates a patient that that's based on features that are and ranges that are in the existing data set, within the ranges that are in the existing data set, and then changes the protected attribute and looks at the difference in time predicted. And our assumption is that, well, given a particular patient and nothing else changes, only their, for example, country of birth changes, then the wait time should not change. But what we discovered is that these models are generating quite different outputs for patients that are exactly the same, but their protective attributes is different. And for example, we had up to 48 minutes on average difference for when we just change the indigenous status in the patient data. So this is my last slide, and I wanted to end it with, and I know this is an optimization kind of focused group, and I probably didn't talk a lot about optimization here, but I think there is, in particular when it comes to testing and AI-based systems, testing optimization is quite important and quite crucial, in particular now with the cost of testing becoming bigger and larger. We need to use optimization to prioritize, to generate better test cases, and to optimize various objectives. In our work, we only have looked at search-based techniques, what I call search-based. It's a term used in software engineering, but mainly based on meta heuristics. There are quite some very interesting problems that I list here, taken from a literature. I did forget to put the link here, but I might include it in the slides before I share them. But there's quite a few interesting problems, in particular when it comes to AI-based systems. Many of them are around the realism. I talked about the test adequacy. So we have diversity and coverage, but we need new metrics for AI-based systems. So we need problems. There's problems around the behavioral boundaries. So how do we generate a diverse set of scenarios that expose different kinds of behaviors? How do we produce high fidelity simulators? The Oracle problem I touched in one of my slides, that's quite a significant one. Debugging such systems is quite difficult. I mentioned some of the problems that relate to this. Because we have a large set of test cases that need to be used to test AI-based systems, test selection, minimization, prioritization is important, regression testing. Once we deploy these systems, we need to monitor them because their behavior might change. And so this is a big area called AI ops, ML ops, the monitoring and testing, online testing. The cost of testing is quite significant still. Optimization can play a big role here. The integration of ML models and metamorphic testing. I mentioned some of the metamorphic testing work here. And then data quality assessments. And particularly, this is significant, in particular if we're using optimization to generate test cases, new test cases. So how do we ensure that they are representative of the entire input space, and instance space analysis can play a big role here. So I will end here with thanking the collaborators that have worked on the papers that I presented here. Thank you.